Good afternoon, everyone. So, in the previous class, we just introduced the term of the what is the chiral center. So, we just introduced what is the chiral center. Okay, and also we have term we have discussed about some of the asymmetric center, chiral center. It is also known as the asymmetric center, asymmetric center, and also it is also known as the. So this term can we have discussed about the what is the actually the asymmetric center or the chiral center. So it can be called as a both chiral center as well as the asymmetric center. And also we have discussed about the trans isomerism, cis trans isomerization, and also the stereogenic center or the stereo center. Also we have discussed about the stereo center, the term the stereo center, and we have discussed one example of the cis trans isomerization. The example was CH3 double one CH3 and hydrogen is the same side. Then it is the cis isomerism, cis isomer. And if we just interchange one of the CH3 and the one of the hydrogen in the position, then we just will get the opposite isomer of this molecule. So now this is act as a this hydrogen is here and the CH3 group is here. Now it is known as the this CH3 group, same kind of molecule, functional group is opposite to each other. Now it is known as the trans isomer. So we have discussed up to this part in the previous class. Now we'll discuss some other interesting thing, which is now here one point is the interesting point is that thus all chiral centers are the stereo centers. So now we can do a comment like now we can do a comment the all the chiral centers, all chiral centers are stereo centers. All chiral centers are the stereo centers. Okay, this is the main important point. Now, but all stereo centers are not chiral center. Now we'll discuss the all stereo centers are the all all stereo centers are not chiral center, are not chiral center. If a molecule contains only one chiral center, then it must be chiral. So if a molecule if a molecule contains only one chiral center, only one chiral center, then it must be chiral. Then it must be molecule must be chiral. But in the other way, if the molecule contains two or more chiral centers, so in other words, we can say if the molecule contains more than one chiral center, then it may or may not be chiral. Then it may or may not be chiral. Okay. We'll discuss the example. Then from that we can understand whether it is true or right, wrong. Now, if we discuss a example based on this parameter, so let's say we have this is the meso tartaric acid. Okay, so here it is the OH and hydrogen is there, and here also another hydroxy group is there, hydrogen, and this is a COOH. Now you can see this carbon center bearing four different atoms. So this is the one chiral center. Same also this carbon center also bearing four different atoms. So it will be also a chiral center. So the whole molecule contains two chiral center. Okay, two chiral center. Now, if we pass a plane, if we pass a plane from this carbon to this carbon, it will be superimposable. So that will be So achiral, so the whole molecule is the, although this molecule has two chiral center, but the whole molecule, the whole molecule is, the whole molecule is achiral due to plane of symmetry. Okay. Now we'll come to the, so this is the example of the mesotartaric acid. So the molecule is known as the mesotartaric acid. Now we'll come to the stereoisomers. The isomers having the same molecular formula but different spatial arrangement of their atoms known as the stereoisomers. Now the another parameter is known as the stereoisomers. So what is stereoisomers? Okay. So stereoisomers, that means the isomers having the same molecular formula, having the same molecular formula, having the same molecular formula, but different spatial arrangement, but different spatial arrangement of their atoms, so that is known as the stereoisomers, that is known as stereoisomers. Okay. Now we will see the, so there are two kinds of stereoisomers. So one is called as a enantiomer. Okay. So what is enantiomer? Enantio enantiomers. So the stereoisomers which are non-superimposable mirror image of each other are called the stereoisomers which are non-superimposable, non-superimposable mirror image enantiomer. So the chirality is necessary and sufficient condition for existence of the enantiomer. So chirality is the necessary and sufficient condition for existence of the enantiomer. So the chirality is necessary and sufficient condition for existence of enantiomer, for existence of enantiomer. So these always exist as a discrete pairs. So how? So let's say for an example, if we have the COOH and here one hydrogen is here and the hydroxyl group is here. Now it is CH3. Now if we pass a plane here, then what we'll see? We'll see the another same kind of molecules. So this is the mirror image of this one. So this is the mirror image of hydrogen and the OH group will be behind this plane. So this is the same molecule. So now these two isomers of the, this is called the lactic acid. This is the example of the lactic acid. Now this is the two isomers of the lactic acid. Two possible isomers. Okay. Now what is diastereomers? So stereoisomers are two types. One is the enantiomer, another one is the diastereomers. So now we'll discuss the diastereomers. So what is diastereomers? So stereoisomers that are no mirror images of each other are called as a diastereomer. So the stereoisomers that are not mirror images of each other, that are not mirror images of each other are called diastereomers. Okay, now if we see the example, now let's say CH3 hydrogen OH, Br OH, this Br means bromine, and this is the CH3. Now if we put a mirror here, now what we will see? We'll see the reflection of this molecule. Now whatever the right side atoms was there, it will be now the left side. So now it will be OH here, hydrogen here, and bromine will come here, and the hydrogen will come here. Now CH3 is also here. Now this is called, it is called as A and B. Now these two is the enantiomer of each other. Okay. Now it is enantiomer of each other. Now this A and B molecules is the enantiomer of each other. Now if we see, okay, now if we just uh, change the position of this molecule, let's say hydrogen OH is here, and hydrogen also it is here. Now Br is here, Br is also here, hydrogen is also here. Now CH3 group is here. Now if we put a mirror image over here, now what we will see? We will see the CH3 group is here and CH3 group is here. Now just whatever the right side group is here, now it will come the left side group, because we are putting a mirror. Now you can see, let's say it is a C and D isomer. Now the C and D isomers also enantiomer of each other. Okay, enantiomer of each other. Now this, the whole molecule, these and this, let's say A or C or B or D, these are all diastereomers. This is called the diastereomers. Okay, so four isomers of the, this, the molecule name is the 3-bromo 2-butanol. 3-bromo 2-butanol. Okay, so 3-bromo 2-butanol existence of the four isomers. Okay, now we'll go to the what kind of molecules it will show the geometrical isomers. So what is actually geometrical isomer? Okay, so although we have discussed in the previous class geometrical isomers and the example of one of the geometrical isomers, but here we will show the other examples like geometrical isomers. Geometrical isomer. So geometrical isomers occurs as a result of restricted rotation. So due to the restricted rotation, due to the restricted rotation of carbon-carbon double bond, restricted, due to the restricted rotation of carbon-carbon double bond, rotation of carbon-carbon double bond. Now this is also called as the cis-trans isomer. Cis-trans isomerism. Now this isomerism exhibit by variety of compounds such as double bond, carbon-carbon double bond. So it can also show, if the carbon-carbon double bond it is there, it can also show carbon-carbon double, carbon and nitrogen double bond, in nitrogen double bond. The compound containing cyclic structure also containing restricted rotation due to their steric hindrance. These are all can also show the this geometrical isomerism. If you see any example where the rotation is restricted due to their steric crowding, then it can also show the geometrical isomerism. Now we have seen the CH3 1 2 butane molecule. So if you see the another example, let's say cyclohexane and one, let's say CH3, this is also above the plane and this is also above the plane. So now this methyl group is there. Methyl means CH3. Okay, so let's say this CH3 group is in the same side, so this is called cis isomer. If it is the trans, that means the opposite one. So let's say one is the above and another one is the trans. Let's say this is the CH3 above. Now this is the trans. This is the trans isomer. Okay. Now it will also show the geometrical isomerism. Now we'll discuss about the conformational isomerism. So what is conformational isomer? So conformational isomers are that can be converted into one by only by the rotation by a single bond. So conformational isomers. Conformational isomers. Conformational isomers is the isomer that can be converted into one another by the isomers are that can be converted into one another by around a single bond rotation. Okay, so let's say for an example, if we consider the example of the butane and what are the conformationals as possible. So that is the one is the eclipsed, another one is the anti, and the third one is the gauge. So we'll discuss one by one. So let's say butane. Butane is the CH3, CH2, CH2, and CH3. Now this is the butane molecule. Now if we see the eclipsed form, okay. So let's say CH3 is here. This is the carbon center. This is the hydrogen. This is the hydrogen. Now this is also CH3. Now another CH2 is hydrogen is here and another hydrogen is here. So this is called eclipsed isomer. Eclipsed conformational isomers. Now if you see the anti one, so in case of anti, that means CH3 is here and one of the hydrogen is here and one of the another hydrogen is here. Now this is the CH3 group. Okay, and another hydrogen is here and another hydrogen is here. Now this is the anti. Okay, so these molecules can be interconverted by rotating around the central carbon-carbon single bond. So these molecules can be interconverted, can be interconverted by rotating around the central carbon-carbon single bond. Okay. Now we'll discuss about the another isomer that is known as the now how to represent a 3D molecule. So let's say we have the representation of three dimensional molecule. Three dimensional molecule. Three dimensional molecules. How to represent a molecule in 3D dimensionally. So now let's say we have so one of the way is the flying wedge or wedge flying flying wedge or flying wedge or wedge dash projection dash projection. One of them is the this flying wedge or wedge dash projection. So how to represent this one? Let's say we have a molecule which contains four different atoms. Let's say not for different metals. So let's say if we talk about the methane, the formula is the CH4. So now how to represent? Let's say let's say let's say CH4. Now C hydrogen carbon contains four hydrogen atom. Now if one want to represent in a three-dimensional manner, then how to represent? So this is the flying wedge way. So where the carbon contains, so let's say two of the armies will be in the planar. So now it is, you can see it is the planar. So the third one will be the below and the above, and the another atom will be the above. Now this is the whole molecule's representation in three dimensional arrangement. Now how to say, let's say solid ways or thick line. So this is called the solid ways. This is the solid ways or thick line represents above to the plane, represents above of the, let's say if it is the plane, this molecule contains a plane, okay, the whole things, then one is the above, another one is the below. Now it is the above of the plane, above of plane. Now if we this is the ordinary line, not ordinary, this is the broken line. So if it is the broken line, it represents below the plane. Now if it is the ordinary line, that ordinary line, it represents in the plane. So it represents the line in the plane, in the, it represents in the plane the whole molecule. This not whole molecule, the line, the ordinary plane will be in the plane. Okay, now we'll discuss about the Fisher projection. So how to represent in the Fisher projection. So the second one, this is the second one. First one is the flying wave, the second one is the Fisher projection. Let's say for an example, we'll go to the example directly. So CHO, if in the exam, if it is written like this way, CH3 hydrogen and CH2OH, then if they ask to represent in the flying wave way, then you can directly write in this way. So this will be the, let's say, below, and this will be the above. This is the OH group, and this is also above. This is the hydrogen group, and this will be the below. This is CH2 OH group. So anywhere if they have given this kind of molecule and they ask to represent in a Fisher way or Fisher projection way, then you can write in this way. So whether, so how to write in the easy way? Let's say if the molecule in the hydrogen, whichever it is in the left side, so it will be in the left side above of the plane, and this line, this is, let's say this is the x axis and this is the y axis. So x axis will be the above plane and the y axis will be the below plane. So x axis above plane, and don't change the position, above plane, and the y axis will be the below the plane. So you can see whatever the in the y axis group is there, so that is in the below plane, and whatever in the x axis atoms was present, so it is in the above of the plane. So, and now we'll quickly go to the another example, that is the Shaw's presentation or formula, how to represent. So in Shaw's formula, in Shaw's formula, let's say if we talk an example where the butane, the simple butane molecule, CH3, CH2, CH2, and then CH3, then how to represent in the Shaw's presentation. Let's say if we have this molecule CH2, now another hydrogen is here, this is the CH3 molecule, we all know that, and also this is the hydrogen, and here it is also another hydrogen, and CH3 molecule is here. So now you can see, so here, so in the whole molecule, one CH3, CH2, two CH2 group and two CH3 group. So here also one CH3, two CH3, and in between this two CH2 group is there. So you can see, so this is the eclipse form of the, or so in the Shaw's presentation, there is also three possible isomers is possible. So one is the eclipsed, and the second one is the anti, and the third one is the gauge. So three isomers are possible. Let's say now if we take this, and this is, let's say it is a one bigger group, CH3 is here. Now this is hydrogen and this hydrogen, and now this is the CH3 group here, and two hydrogen will be. Now you can see this CH3 and this CH3 anti to each other, so you can easily say this is the anti-isomer of this Sauer's presentation. Now if you see, this is the eclipsed and this is the gauge. So what will be the gauge presentation? In the gauge presentation, so let's say CH3 is here and also CH3 is here, but the hydrogen is the equatorial to this one. Now this is the gauge and this is the eclipsed. So this is the eclipsed isomer, this is the anti-isomer, and this is the gauge isomer. And the third one is the Newman projection. So in the beginning I discussed about one example, and that was the Newman projection. And the third one is the Newman projection. Okay. In the Newman projection, so whatever I discussed in the beginning, so let's say we have this hydrogen and CH3. Now let's say here it is a CH3, hydrogen is here and hydrogen is here. Now it is the eclipsed isomer. So in general, people are worried about this eclipsed and the anti-isomers. They won't discuss about the much more in the gauge. So this is the anti-isomers. So okay, now you can see this is the anti-isomers. This is the gauge and this is the anti-isomers. Okay, now we'll discuss a little bit about the plane of symmetry. Now what is the plane of symmetry? Let's say we have the now the elements of symmetry. What are the kinds of elements of symmetry present in the organic chemistry? So elements of symmetry. So elements of symmetry offer a simple device to decide whether it is a chiral or achiral. So elements of symmetry offer a simple device whether simple device uh, whether the molecules is whether the molecule is chiral or achiral, whether the molecule is chiral or achiral. Okay, now we'll discuss about plane of symmetry. So what is plane of symmetry? So the plane of symmetry, the plane which divides a molecule into two equal halves. So the plane, so the plane which divides, which divides a molecule into two equal halves is known as the plane of symmetry. So now we'll discuss the previous example whether I have shown the molecule contains two chiral center but is still a chiral due to the presence of the plane of symmetry. Now you will understand clearly that whether it is what kind of plane of symmetry is present. So let's say this CH3 molecule is here and hydrogen OH, hydrogen, now another hydrogen OH, and here it is a CH3. Now see, this is the two chiral center, but it still contains one plane of symmetry. Why? If you pass a plane from this way, then you can see the two same equal halves of this molecule. So this is the plane of symmetry. Although so although this molecule has a two chiral center, but still, although the molecule has a two chiral center, but still it is achiral. Okay. So in this class today, thank you.